Now we continue the same reaction of that we studied before, hydrogenation in water or alcohol as solvent. Now what's going to happen? Hydrogenation in water or alcohol as a solvent, in that case we have different issues. Now first of all, as I mentioned to you, water or alcohol as a solvent, we have polarity, polar solvent. And if you use the HBr, HCl, HBr and HI are considered strong acids in water, right? pK like a -7, -8, -9. Having said that, they are not going to be staying as a HCl anymore. HClAq suddenly becomes H3O plus Cl minus. So the reaction is going to be slightly different now. So let me, and also if water is a solvent, let's think about the proportion of H2O with respect to this one. It is like in a swimming pool. Think about yourself in a swimming pool. How many molecules of water versus how many you? For every one of you, there are how many? You cannot count, because you know, in one single drop of water has probably 10 to the 20 molecules of water. So we're not talking about one drop of water in a swimming pool, isn't it? So we have a whole lot of water there. So in that case, the law of mass action, you know about Le Chatelier's principle, right? The law of mass action is going to take over. In that case, solvent can also function as a nucleophile. Remember, H2O or CH3OH, they have lone pairs which are an anatomy necessary for nucleophilic behavior. But are they as good a nucleophile as OH minus? No. They are not as strong a nucleophile as OH minus or methoxide. Hydroxide or methoxide are stronger. These are stronger nucleophile. But what are we contrasting? We are contrasting CCl4. Contrasting CCl4, which was not capable of behaving as nucleophile at all, because all you have is chlorine here, a chlorine here, and you have a chlorine here and a chlorine here, right? So it's completely non-polar. It has no electron. There's a lot of electrons here. We got a whole lot of electrons, but none of these chlorine atoms are willing to provide any electron interest in the reaction. So here we have a different drama. The drama here is, if I take the same molecule now, treat it with HBr and H2O, strangely, the product we are going to get is not going to have anything to do with the chloride or a bromide or iodide. It's going to be that. How could that be? How would you get this as the product in this reaction? This is the overall product. So we have to justify it. Remember, we have to come up with a mechanism. Mechanism is a storytelling. We put this one in a pot and we got this. How did we get that? So here is the story. Well, I can start the same way, because HBr, are we going to write like this? What is appropriate? Just like in HBr, is it appropriate to like this? Or is it appropriate to write like this? That's more appropriate way. This is not happening in water. This is okay in CCl4. That is okay in CCl4. This is not okay in CCl4 in water. So this is not okay in water. Okay, so if it is water as a solvent, this is what we are supposed to write. So this is not acceptable. So ultimately, what is going to happen? We are going to see a Regio selection. If I simply say OH2, positive charge here, and put a transition state on that, this can now give you a Regio selection. Regio selection is going to be H adding here, positive charge on this one, while adding H here and positive charge on this one is to be slashed. That is not going to happen. We are going to cancel that. We are going to say this is not going to happen. This is what? That cross is representing Regio selection. That's a Regio selection. Okay? Now what we are going to do? At this point, who is going to come in? Think about what happened to bromide in the pot. See, when we added HBr plus H2O, right? It gave you H plus AQ, which is H3O plus, and also gave you Br minus AQ. That means what is Br minus now? Br minus is also floating in a ocean of water molecules. So that Br minus is being entertained by whole lot of water molecules surrounding it. Delta plus, delta plus, delta plus, delta plus, delta plus, delta plus. That means it's a solvated bromide. Is it really interested in reacting? No, it's very comfortable. It's very comfortable. But somebody has to come in and rescue this carbocation. And when bromide is far away, right, when it is not interested, one of the water molecules says, how about me? Because it's in large quantity. So water molecule can do this. Of course, it can do both. This can this side or this side. That's a stereo issue, right? That's a stereo issue. And knowing already H is not going to offer a whole lot of resistance, it's a 50-50. Okay? So I'm going to continue that story here. So what would you have now? You would have, that if I go flat planar. So if I had the first H added here, and that's the H, that's another H, right? Now, since I have a OH2 from the top, I might get, if this is the carbocation, what did I write here? These are Me, this is Me, okay? So now if you can have H2O come from the top or from bottom, that will give you two choices of stereo product. In one case, it's going to be theoretically or in practically it makes no difference, but we have to finish this storyline. So one attack is going to be like this, right? And the other attack, this is a solid, Me. The other one will be from the bottom. That means we will have a O, H, H, and then now in this case, since both of them are Mes, that's where we don't have a stereo issue. But the drama is going to be still the same. Molecular games are still going to be the same. We didn't finish the reaction yet because in this case, water attacked. The problem is now water has a problem, started screaming, who took my electrons? Somebody has to escort this proton. So another water molecule, right, has to come and grab that hydrogen and give those electron backs to oxygen. Similarly, a different water molecule has to come in, right? And you know, this functions as a who and this functions as who. There are two water molecules in this game. Each one of them is, this is a nucleophile and this is a base. Why one of them is called nucleophile, why other is called a base? Because of the job. The job of this water is to go and get married with this carbon and stay there. Job of this water is come and grab a proton and walk away. In this case, is this hydrogen offering any resistance? These hydrogens are not offering any resistance, so that is why you are going to get a 50-50 mixture of, so final product is going to be a 50-50 mixture of a, I'm just going to write CH3, right, that's a CH3, and then you can say OH here, Me, and here it's going to be CH3, Me, and a OH. Turned out to be 3 methyl groups on that carbon. That's not the issue here. Ultimate answer is OH. Now, you see, this is what I said. What happened to that bromide? What happened to that bromide? Bromide is still hanging around water molecule. This is a water solvent. So it's going to be there and it's going to be entertained. It says, I'm not interested in reacting because bromide in water is very stable ion. So, will hydrohalogenation give anything to do with the halogen and the final product? No. The moment you have water, that's what's going to happen. And I can show what happens if an alcohol is the solvent. Same case. What do we say? If alcohol is a solvent, right? If alcohol is a solvent, now what's going to happen is, let's say HCl in CH3, CH2, OH. Consider. The product is, if you noticed what the product in this case was, and even if you didn't know it, there is a H added. There were only 2 hydrogens here. There are 2 hydrogens still there, and the third hydrogen was added. We didn't really have to write that, but that's the new thing that was added. But if there was HBr, Br did not come in because of water. So the OH came from here. If OH came from here, that means we lost one of the hydrogens. What do you think you are going to get? We are going to get this as a product. O, CH2 and CH3, right? That is the ultimate answer. So for most part, you are supposed to identify this as the answer for this question. Okay? Test is not always the goal, but test is the only way we can assess whether you learned it or not. How did this happen? How did this happen? We know that when we first attacked HCl, right? Now even if you showed like this, it's not a big deal. It's not a big deal. That's fine. And we will say that we already selected, right? Let me say I did a selection and crossed the selection that I'm not going to use, and that is my product, right? That is my product. The intermediate. That's the only intermediate. Which one am I going to crossing? Which one am I crossing out? I'm crossing out this one. I'm crossing out this carbocation. I'm crossing out because this is primary, this is tertiary. Okay. Now, instead of water, we have a O, H, CH2, CH3 functions as a nucleophile. When this attacks here, and I'm going to skip step because that H has to be taken away by another nucleophile or another base. So your final answer is going to be now O, CH2, CH3. And we can always say that is a mixture. This is a stereo mixture. Now in this case again, this is not a chiral center because there are 2 methyl groups on the same one. So I just simply said stereo mixture. It's not racemic mixture and it's not chiral. So the product has to be understood. Just to give you an example to be kept in mind. Alright, let's say I have this molecule. This molecule has two double bonds. This is an example of question. Okay, there are two double bonds, and if I reacted with this HBr in CCl4, what do I get? If I react this one with HI in water, no, CH3OH, what am I going to get? Okay, and this should be a very quick process. Now, while we did not study what would happen if there are two carbocations, if there are two alkenes and they are isolated, they are not conjugated with each other. That makes our life a bit easier. Both of them are going to react. Doesn't matter which one, and both of them happen to be, both of them are non-symmetric. Both of them are non-symmetric, right? So it's much easy for us to say the product is going to be exclusively this. Br here and Br here. Okay, because you added H here, and you know, if there are two possibilities of carbocations, you are going to form carbocation here. If there is a possibility of forming carbocation here or here, you do it here. That's why when the carbocation is formed, if I'm predicting what was the intermediate, here was the intermediate. This was an intermediate. That was the intermediate, right? This was the intermediate. And if this is the same intermediate in this reaction also, this is an intermediate. Now, let's think about it. Is it possible to have both of them at the same time? No. That means having a molecule with two positive charge is unlikely. So this may not be the real intermediate. What could be the intermediate? It could be that. Okay. And that didn't react yet. That means it finishes the reaction here, then reacts here. Or finishes the reaction here, then reacts here. Right? So the likelihood of this being an intermediate are slim because two positive charges, two debts in a molecule, two debts, I'm talking about debt, D-E-B-T. Positive charge means debt. There is a loss. Two losses are not going to be easy to do at the same time. So the real intermediate might be either this one or this one. Step number one. Of course, step number two would be reacting with second one. So we don't worry about, we don't know which one is which. We don't know whether this happens and then this happens, or this happens then this happens. We don't know. Ultimately, in the part, you will have this as the product. How about this one? In this case, our product is going to be, right? It's going to be OCH3 and OCH3. Okay? What about that I? What about that Br? Well, occasionally that I might actually react. So you might have a little bit of contamination in the pot where one place or the other there could be iodine. But that's not something we need to worry about. This is the major product. Okay? We just focus on major product in our conversations. Okay? Major product is, I would say, 99+%. There is always a chance of having tiny bit of other products. So what would happen in this case? What would happen in this case? If I have two locations and neither of them are regio selective, in that case, if I react with the HBr in CCl4, right, what do I get? I will get, one instance, I may have Br here and Br here, right? Those two are same thing actually. They happen to be the same, but then if they further react, that's one molecule. If they further react, what would I get? Now we will have difference. Now we will have, let's say I have a Br here, the one Br can add here and the other Br can add there. Now these two are different. These two are different because this is a 1,4 dibromo, this is a 1,3 dibromo. So you will have products like this. So if I have multiple pi bonds and if they are not connected by, they are not conjugated, then HBr will continue to react even if I have 10 pi bonds. Suppose a molecule like this. Now this is where the hydrogenation of oils come in. Hydrogenation of oils. When somebody says partially hydrogenated oil, that's a joke because there is no such thing as partial hydrogenation. Either you do complete hydrogenation or no hydrogenation. So the difference between oils and fats is fats are completely hydrogenated ones. Okay. Suppose I have these many 5 pi bonds, and if I added Hi in CCl4, which am I going to pick to react? I don't have a choice. I can pick any and all of them. So essentially we will have every one of them will add one iodine. In this case I'll add iodine here. In this case 50% here, 50% here, 50% here, 50% here, 50% here, 50% here. Iodine here, hydrogen here, right? In this case because these are symmetrically substituted. Those three are symmetrically substituted. So we will have a blend of many products. Okay, keep that in mind. People will not be, I will not be asking you, I cannot ask you a question like this unless I'm ready to evaluate 7 or 8 different products here. Okay, because this one is guaranteed to be iodine here, this one is guaranteed to be iodine here, no question. See, in this case that was easy. Bromine has to go here, bromine has to go here. That is a requirement. By the way, this is where a term called Markovnikov rule comes in picture. Markovnikov is a Russian scientist who made a very interesting observation. At that time, I'm talking about a couple hundred years ago, right? At that time, carbocation concept was not known. So Markovnikov said this. What he said was, when an unsymmetric, see, has a key here, when an unsymmetric alkene is reacted with HBr, so that was his key pet molecule, that was Markovnikov's pet molecule, HBr. Now we since know that HI and HCl can do the same thing, right? When unsymmetric alkene is reacted with HBr, H, this is what his language was, goes to the less substituted carbon and Br goes to the more substituted carbon. Now if you look at it, this is exactly what is happening when we talk about carbocation. See, if I simply take this molecule and added HBr, according to Markovnikov, H goes to the less substituted. Remember, there are 2 hydrogens, right? This is more substituted because there are 2 alkyl groups. So what he said was, you are going to get H here and Br here. Did we come up with the same answer? Yeah, we did. We did. So we came up with the same idea, except Markovnikov was able to do this without a concept of carbocation stability. We have learned about carbocation stability, right? Markovnikov did not know. So the concept did not what do you call it, was before carbocation identification. So Markovnikov made a rule, so we still consider this as a Markovnikov rule. And if there is ever, and we are going to find there are cases, if there is ever is an opposite product. What do you mean by opposite product? Or something that goes against the product would be adding Br here and H here would be anti-Markovnikov product. This is Markovnikov product. Anti-Markovnikov because it went against Markovnikov's rule. How did it go against? Well, the Br was added to here. Br is added to less substituted carbon. Okay, so in normal circumstances this should not happen. That's why it's against the Markovnikov rule. But if there are some unusual circumstances where this happens, we'll come across that. But Markovnikov, so you can see Markovnikov rule essentially talks about what? Regio selection. Right? It matches with Regio selection based on Markovnikov rule is by itself. It has nothing to do with Regio selection. But we now do this based on carbocation selection. So both of them match. They are both equivalent. Now that is a very simplistic situation and dealing with HBr. Now carbocation selection can be used for all circumstances. This is more universal. Markovnikov didn't say anything about this reaction. He could not say anything about this reaction because look, when HCl is added to an unsymmetrical alkene, where the heck chlorine go? Chlorine didn't even go to carbon. H did go here, but chlorine did go where? It went somewhere else. So Markovnikov was not able to answer, or Markovnikov cannot be used to explain this product. But this product is called Markovnikov product because it kind of matches with his concept. Because the first adding group is H. First adding group is H in this case. Is that correct? The second adding group is this one. The second group that was added is this one. First adding group was this one. Then second adding group was this one. So essentially what Markovnikov said was H adds to the less substituted carbon, then Br goes to more substituted carbon, right? That is a better way of saying it. But Markovnikov is not alive to make that correction anymore. But we still give him credit, just like Bohr model. Is Bohr model final answer? No. Is Dalton's theory the final answer? No. Most of those theories have been since modified with the current knowledge. The modern theories are slightly different, but Markovnikov is still very prominent person in alkene addition reaction. So we do use Markovnikov product as long as it fits the narrative. It fits the narrative that carbocation stability is followed. Now, followed in this manner. Okay. We are going to follow carbocation stability, but still we might get anti-Markovnikov product. That's something we are going to come across. Okay. So far what we have done is we have looked at alkene reaction in case of alkene reaction with HX in CCl4, and we looked at HX in water or ROH, right? We have done those two. What is remaining? Just want to give you a forecast of what is coming. What is remaining is we will be now talking about X2 in CCl4 and then X2 in water or ROH. In the same context, we are going to write something called, we are going to look at NBS, that's N-bromosuccinimide in H2O. So those reactions are going to be next set, right? And then we are going to look at another set of reactions where HX in H2O, HgOAc twice in H2O or ROH, part 1. The second step would be sodium borohydride. And the third reaction in that category is BH3 THF, followed by H2O2 NaOH. Okay, those three fit in one narrative. These three fit in one narrative. These three fit in one narrative. Then, so we are done with this. This is one type of family. This is a second family. This is a third family of reactions. They have a similarity. The fourth one is with the Br2 HNu and NBS HNu. So that's another family of reaction. Okay. The fifth family of reaction is going to be H2 PTC ethanol, 0 degrees Celsius. This is a family by itself. Okay. Then there is another family we are going to react, which is KMnO4 under mild H plus or OH minus condition, or osmium tetroxide in presence of NaHSO3. This is a family of reaction. Okay. Then there is another family. Another family is take an alkene, react with CH2I2 zinc, or react with KOH comma CHCl3. That's another family. Okay. And what is remaining? Then we have a reaction where we take an alkene, treat it with O3, ozone in THF, and step number 1. Step 2 is zinc HCl, or we can also use permanganate with heat NaOH. So this is another family of reactions. Okay, so we have these many families. We just considered that one. We have these many individual families that with close similarity to each other are going to be discussed. Okay, so I'm going to pause right here.